Our next speaker is Luigi Andolfato. Sorry. Luigi is a software engineer working at ESO since 2003, mainly on telescope and interferometer control software. Before joining ESO, he worked for Motorola in the UK, Siemens in Italy, Quark in Germany, and the University of Washington in Seattle. And his talk is about behavioral models for device control.
Thank you. So, good morning. This presentation is about promoting the exchange of models within the scientific community. Why models? Well, if you have a piece of code that runs on a software platform like Tango or EPICS or even TwinCat PLC, and you want to reuse it on a different platform, then you will need to port it. And the porting is going to cost because of the dependencies that the code has on libraries and technologies which are specific to the source and target platform. So models instead, they are at a higher level of abstraction. So they contain less details, and in principle they could be ideally platform independent, so much easier to port. And because they contain less details, they are also easier to understand. So our initial contribution to this initiative of exchange models is a library of behavioral models, actually state charts models, which describe the behavior of some some devices which are commonly used in control system, like shutters, lamps, motors, and piezo. This library has been developed at ESO by the Instrument Control Software Group. After several years of experience in supporting consortia to build instruments for the Very Large Telescope. So, in order to exchange models, first of all, we need to create them. We need a language. A language is two things, basically, syntax and semantic. I don't know why, but in the modeling community, there is the tendency, or the feeling that there is the tendency, is to concentrate more on the syntax than on semantics. But it's actually extremely important to have a precise semantics, and I will come back on the next slide on this point. But this is to avoid, let's say, misunderstanding. The other important point is when we created models is to avoid to put information in the models which are platform dependent. This is simply because we want to facilitate the reuse of the models on different platforms. And finally, what we need is to decide on an exchange format, so a way to exchange models. And ideally, this should be independent from a commercial tool to avoid vendor lock-in. So, our models are use the state chart notation, which has been introduced many years ago in the 70s, late 70s by David Harel. It's a combination of the Mealy and Moore state machine plus some more features like orthogonal region and composite states. So the syntax is well established, but unfortunately there are several implementations. The semantic was never precisely standardized. To give you an example, let's look at this simple model. You have a state with an entry action, which is just a piece of code that you have to execute when you enter a state, and an exit action, which is again a piece of code, and the do activity. Do activity models a long-lasting task. Usually it's mapped to thread or non-blocking code like can be implemented with fibers or coroutines. So the standard says, or let's say the syntax says, okay, when you exit a state, the do activity has to terminate, but it doesn't say whether it has to terminate before or after the execution of the exit action. So you have some implementation that will stop the do activity and then invoke the exit action, and others which will first invoke the exit action and stop the do activity. And this creates a problem, especially when you implement the do activity with threads, so you can have bad surprises. So it's extremely important to have a well-defined semantic for the modeling language. So there are several implementations of state chart notation, and we have evaluated 3 of them. One is probably the most common is the one that you find in the state machine of SysML UML. So SysML UML is an object management group standard. It has many years. The syntax is well established, but the semantic, believe it or not, is not standardized yet. Last year, or actually 2 years ago, they started a precise semantic for state machine working group, where they are gonna standardize their semantic, but unfortunately, no result has been published yet. So, since our devices usually they are implemented via PLC, we had a look also PC UA. PC UA is to allow communication to the PLC. And it's from Open Foundation, and they have, in the specification, they have a layer which is called data layer, or a section which is included the data layer. And there they describe also state machine, but it's actually a subset of this, it includes, or specify a subset of the state chart features, and there is no semantic specification. So we have decided to go for SXML, which is state charts XML. This is a recommendation from the World Wide Web Consortium, the same that has standardized HTML and JavaScript. And they provide a well-defined syntax using XML, which is easy to exchange, by the way, and a precise semantic in the forms of test cases. So they provide the test cases and they expected the result. So this was the work to standardize SXML starting in 2004. And in 2015, they released the recommendation. So this is now a standard, at least for the W3C. Now, all our models, they share some common principles. So let's say we have adopted some rules. The first one, so here I will just explain a few of them. The others are in the paper. The first one, quite important, is to decide what a state represents. So our state machine, they have states. The states usually represent the status of our system, but our system in this case is a device, which is software and hardware. So does a state represent a hardware or software or both? Well, one possible approach is to have one state or one set of state to represent the hardware. Like you have here in this model, the first region, the first part of the model here represented the hardware. And then you have an orthogonal region, which is representing, including the state of the software. So orthogonal region is just, is like having two state machines combined, close together. So that means that your application will have two states. It will have, for example, ready for the hardware and ready for the software. Now, this seems to be a clean and neat solution. However, increase the complexity of the state machine. So you end up to have a lot of states. Another possibility is to combine the two. So to say, okay, a state here, like not already or initializing, represents both hardware and software. However, if you go for this way, you have to decide what to do when the hardware and software states do not coincide. Let's take, for example, a shutter. You send a command to the shutter to open, and the command succeeds, the shutter opens, so up to now it's fine. Software and hardware state coincide, they are open. But then somebody goes to the lab and closes manually the shutter. So in this case, the hardware is closed, but the last command, the last software command successfully executed was open. So in this case, they do not coincide anymore. And so to solve this problem, we give priority to the hardware so that because in this case, at least for us, it's more important to have the status of the hardware. The other rule that we adopted is is to split our models in two parts, basically. One contains the model of the general behavior for all the type of devices. So we have abstracted for all our devices a model, which is actually this one, but consists of two composite states, standby operational. Standby follows the initialization of the device, and operational instead is when the device is going to be used, or can be used, actually, during operation. And then there is a set, a specific behavior which is specific for all type of for the different type of devices. So, like for the shutter, you will have the shutter can open, close, a lamp will be on, off, etc. And how do you model this? So one possibility is to have a composite state, so sub-state in operational, for example. You can put here your shutter open, shutter closed. Or the alternative is to have an orthogonal region. So you put this one in one region, and you add in another orthogonal region that has the specialized states. If you do so, however, you will end up with some state that may be inconsistent, like you are, for the general behavior, you are ready, and for the operational state, you may be in moving, for example, for a motor. And to fix this problem, you have to use guards. So at the end, you end up with a more complex model. That's why we decided to go for the specialized state with the substates. So the last guideline that we had considered is how to do failure management. So we identified two goals. One is for the initialization phase of the devices. And in this phase, we want to prepare the device or prepare the system to be reliable for operation. So our goal is to increase system reliability. So if a failure happens, we try to reinitialize the device, for example. While in operation, the goal is to increase the system availability. That means that if a failure happens, for example, we don't reinitialize the device, but we try to send, for example, again, the same command, or to wait until to see whether the hardware recovers. So this is an example of a lamp device. I will not go into details. You find the description in the paper. But even a simple device like a lamp that goes on-off can have some interesting behavior. So to build these models takes time. You have also to test them. So the idea is, why do we need to do over and over again the same models? Why don't we have a library of models that we can just look around and pick up the one that we need? And what we can do with the models, well, nowadays you can do a lot of things. You can apply model transformation and get code out of it. You can apply formal verification. You can easily execute the models. For example, SXML is interpreted state machine, so it's not compiled. You can load it in a SXML engine and run it immediately. And if you implement the action and the do activity, you can get a simulator out of it. But even the simplest way of using a model, just to copy and paste it into your design document, can help in saving time. So this is my last slide. The models are in a repository. GitHub is OpenMBE, is a model-based engineering environment. Is a repository created by NASA JPL. And I invite you to have a look. There are a lot of tools for modeling. There are also models, not only ours, but also models from other institutes. And our models are under the Komodo tool, which is a model transformation tool that can be useful also for you to have a look. If you need an example how to do model transformation, there you have an example. And we support some platforms, so we can generate code for some platform like VLT, ACS, Java Pathfinder, Model Checker, and so on. Thank you for your attention.
We will only have time for one question for Luigi. There's one on my left-hand side.
Hi. So how do you verify that the implementation and the model, or two different implementations in two different platforms, they have the same behavior?
This is why the semantic is important for the state machine. So what we can do is, if you adopt SXML, you should try to get an SXML engine on both platforms. So, for example, there are several implementations of SXML for different languages, but if the implementation, if it's certified, then it should behave in the same way regardless of the platform is it run on. Then this is true for the logic of the state machine. What you will still have to do is to do the porting of the actions and do activities, and for that, there is no immediate verification. You have to do it with your own test case, unit test and integration test.
Let's thank Luigi again.